Okay, so in this video, we are going to consider examples of the following question. And the question is, are the following vectors linearly independent or dependent? And we're using the term here vector, thinking of vector spaces. So even though we will be considering matrices, polynomials, rational functions, and other more complicated functions, we know that these spaces, spaces of matrices and functions, are spaces that are called vector spaces. And so even though the elements do not look explicitly like vectors, we can think of them as vectors. Now if you remember, when we try to determine whether vectors from a vector space are linearly independent or dependent, we simply consider a linear combination of these vectors giving the zero vector. Suppose we have n such vectors, and we consider a linear combination of these n vectors, giving the zero vector. So we have, say, n vectors from a vector space. The vectors are v1, v2 up to vn. We consider a linear combination of these n vectors, so c1, c2, cn are real numbers. They are the coefficients of this linear combination, giving the zero vector. Now, if the only solution is the trivial solution, where c1 equals 0, c2 equals 0, up to cn equals 0, then the vectors are linearly independent. On the other hand, if we can find a non-trivial solution, so a solution to this equation where at least one of the coefficients, whichever one it is non-zero, then we have more than the trivial solution, and so the vectors are said to be linearly dependent. So here's our first example. We'll consider three 2 by 2 matrices. So our first element, 1, 2, 3, 4. Our second element, 1, negative 1, negative 1, 1. And our third element, negative 1, 13, 10, 8. So again, here we can think of our vector space being our 2 cross 2, so the set of all 2 by 2 matrices with real coefficients. And therefore this is vector v1, say, our first element. This is vector v2, and this is vector v3. So we go back to the definition. So are these three matrices linearly dependent or independent? So C1, V1, so C1 times the first matrix, 1, 2, 3, 4, plus C2 times V2, the second matrix, 1, negative 1, negative 1, 1, plus C3 times the third matrix, negative 1, 10, 13, 8, equals the zero vector. Well, the zero vector is always the zero element of your space. Our space is a space of all 2 by 2 real matrices, and so the zero element is the 0 2 by 2 matrix. And the question is now, how many solutions for the coefficient C1, C2, C3 does this equation have? Well, if you notice, if we collapse this linear combination as a single matrix, we will obtain the following matrix. Entry 1, 1 will be C1 plus C2 minus C3. Entry 1, 2 will be 2C1 minus C2 plus 10C3. Entry 2, 1 will be 3C1 minus C2 plus 13C3. And entry 2, 2 will be 4C1 plus 1C2 plus 8C3. And if you look at this now, after we combine our linear combination into a single matrix, this matrix equals the zero matrix, but they can only be equal if they have the same corresponding entries. And so this must be 0, this one must be 0, and the same goes for the other two entries. So all of these must be 0, and we get therefore a linear system. In 4 equations, and 3 variables. So let's solve the system. I'll write already the augmented matrix of the linear system to save ourselves a bit of writing. Coefficient C1, C2, C3. As we have just said, this must be 0, so 1C1 plus 1C2 minus 1C3 equals 0. 2C1 minus C2 plus 10C3 must equal 0. 3C1 minus C2 plus 13C3 must be 0. And finally, 4C1 plus C2 plus 8C3 must also be equal to 0. And now we can solve for the coefficients of our linear combination by simply solving the linear system. Let's row reduce. So we can do row 2 minus 2 row 1, row 3 minus 3 row 1, and row 4 minus 4 row 1, as we already had a leading 1 in the top row. We copy the first row as we're not changing it. So 2 minus 2 is 0. Negative 1, negative 2, negative 3. 10, negative 2 times negative 1 is 10 plus 2, 12. 3 minus 3 is 0. Negative 1, negative 3, negative 4. 13, negative 3 times negative 1 is plus 3, so 16. 0, zeros remain zeros. And finally, 4 minus 4, 0. 1 minus 4, negative 3. 8 minus 4 times negative 1 plus 4, 12. And 0 stays 0. Well, we have our first leading 1. We've killed the entries below. Now we repeat. Before, and here we'll tweak our solution a little bit. We won't get a leading 1 first. We'll kill row 4 and then turn this into a leading 1. So I'll abuse the notation a little bit here. I will do row 3, row 4, minus row 2. And now I'm abusing notation. I will then multiply row 2 by negative 1/3. So a slight abuse, but this will save us a bit of writing. So we copy the first row, as we're not changing it. The third row as well, we're not changing it. Let's perform this operation. So row 4 minus row 2, but they're the same, so row 4 becomes a row of zeros. And if we multiply now row 2 by negative 1/3, it becomes 0, 1, negative 4, 0. We have our second leading 1. We can now kill this negative 4 by doing row 3 plus 4, row 2. So we can recopy row 1 and row 2 as we're not changing them. Row 4 as well is a row of zeros. And now let's see, 0 will stay 0. Negative 4 plus 4 is 0. 16 plus 4 times negative 4 is negative 16, 0. And so row 3 becomes a row of 0 as well. We're almost done the reduction. Finally, we do, well, we can't get a third leading 1. And so we can do row 1 minus row 2. And this will then give us the reduced echelon form of our augmented matrix. So 1 minus 1, 0. Negative 1, negative 4. Negative, negative 4 will be plus 4, so therefore positive 3. And now we have the reduced row echelon form of our system. Well, let's write our complete solution set, and if you notice, C3 doesn't have a leading 1, and so it is a free variable. So right away, we know that we will have linear dependence. Because C3 is a free variable, it will become a parameter which will give us an infinite number of solutions, therefore more than the unique trivial solution. Let us write our solution set here. So C1 equals, C2 equals, C3 equals. Well, C3, as we said, is a free variable, so we can call it T. Then we can solve for C2 as being 4C3, therefore 4T. And we can solve for C1 being negative 3C4, negative 3T. And again, T is a parameter, so it can range over all real numbers. So we have an infinite number of solutions. Therefore, the original three matrices are linearly dependent. And this is our conclusion. I'll just rewrite the matrices. So 1, 2, 3, 4. 1, negative 1, negative 1, 1. Negative 1, 10, positive 13, 8. These are linearly dependent. And if you want to give a non-trivial solution, well, it's quite easy, right? For any value of t, if you replace C1 by negative 3t, C2 by 4t, C3 by t, these three coefficients will be solving this linear combination. And so you can take, for example, t to be equal to 1, then you'll have negative 3, 4, 1, and plug in here negative 3, 4, 1, and see that once you add the three matrices, you get the zero matrix, which gives you an obvious non-trivial solution to your linear combination, giving you the zero vector of your vector space. And that's just one example. Let's do one more example, but now instead of looking at vectors being 2 by 2 matrices, let's look at our vectors being polynomials. The question is the same. Are the vectors, the elements of our vector space, linearly dependent or independent? This is B. So we'll take here three quadratic polynomials. So say x squared minus 3x plus 1, x squared plus 5x minus 3, and finally 3x squared plus 7x minus 5. So we have three polynomials. And now here, your larger vector space, you can take several examples. You could take the space of all functions as a really big vector space. You could take the space of all polynomials, or you could take an even smaller vector space, simply P2. Right? We're considering quadratic polynomials, the degrees at most 2, so all of these are elements of P2. If you remember, the set P2 is a vector space that contains all polynomials of degree at most 2 with real coefficients. So we have our vector space, and those are the three elements. And again, we could call them v1, v2, and v3. The three vectors from our vector space that is P2. As always, we consider a linear combination of these three vectors giving the zero vector from the vector space. So C1 times V1, x squared minus 3x plus 1, plus C2 times V2, x squared plus 5x minus 3, plus C3 times V3, 3x squared plus 7x minus 5, being equal to the zero vector. Well, we have a space here of polynomials. The zero vector is the zero element. the zero polynomial. Therefore, this is simply equal to 0 for all values of x. As I've said, the zero vector from the vector space P2 is the zero polynomial. So this is true for all values of x in the reals. If you haven't seen this notation before, the inverted uppercase A, this means for all values of x in the real numbers. And now the question is, well, how do we solve for this linear combination? The idea is regroup similar powers of x, right? You'll have a quadratic term, c1 times x squared, so it's c1, plus c2 times x squared, plus c2, plus 3c3 times x squared. So that is the coefficient of the x squared term, c1x squared, plus c2x squared, plus 3c3x squared. Plus, what about the multiple of x? Well, negative 3c1 plus 5c2 plus 7c3 times x, and the constant term plus c1 minus 3 c2 minus 5c3. And once again, this equals the zero polynomial. But if you think of it, the zero polynomial is the polynomial where all the coefficients are equal to 0. So the constant term must be equal to 0. The linear term must be equal to 0. And the quadratic term must be equal to 0. This is the only way to obtain the zero polynomial. And if you notice, once again, we have a linear system in the three coefficients c1, c2, and c3. So we can solve for those coefficients by solving the corresponding linear system. Let's construct the augmented matrix. Now we only have three equations. So the first equation, 1, 1, 3, this equals 0. Second equation, negative 3, 5, 7, and that's equal to 0. And the third equation, 1, negative 3, 5, and that's also equal to 0. We already have a leading 1 in the top row, so we can do row 2 plus 3 row 1, and row 3 minus row 1. To kill the entries below our leading 1. The zeros will always remain zeros. Recopy the first row as we're not changing it. Let's perform the operation. So we'll get 0, 5 plus 3, 8, 7 plus 6, 13. Oops. 1, negative 3, negative 5. Okay. So row 3 minus row 1, so 0. Negative 3, negative 1, negative 4. Negative 5, negative 3, negative 8. That's equal to 0. Let's get our second leading 1, but what we can do here is we can kill off the 8 with the negative 4 by doing row 2 plus 2 row 3. And then I'll abuse a little bit. I'll swap row 2 with row 3. The zeros remain zeros. My bad. 7 plus 3 times 3 is 9. 7 plus 9 is 16. Right, now we're talking. So if I do row 2 plus 2, row 3, I'll get 0 plus negative 8, 0 plus negative 16, 0. So this will become a row of zeros. And this row will become in place of row 2, negative 4, negative 8. And now let me multiply row 2 by negative 1/4. We have our second leading 1. And let's kill this 1 by doing row 1 minus row 2. And once again, we will have linear dependence. C3 is a free variable, which will give us an infinite number of solutions. Let us write our solution set. So C3 is free. It becomes a parameter, say t. Solve for C2 as negative 2C3, therefore negative 2t. Solve for C1 as negative C3, therefore negative t. And t once again can range over all real numbers. As we have an infinite number of solutions, we obviously have more than the trivial solution, and so our three polynomials are linearly dependent. So here I'll be a little lazy. I'll just simply rewrite v1, v2, and v3. And if you wanted a simple non-trivial solution, you could take t to be simply 1 or negative 1. Say you take t to be negative 1, then you will have the solution 1, 2, negative 1. And so if you would do 1 times v1 plus 2 times v2 minus a v3, and you can check, you will arrive at the zero polynomial. And you see, in both cases, whether we had matrices or polynomials, we were able to check linear dependence or independence by solving a corresponding linear system. In our next video, we will consider examples of more complicated functions where we cannot always use or reduce the problem to solving a linear system, and we'll have to be a little more crafty, and this will be the topic of our next video.